Perfect. Okay, let me start by thanking the organizers for setting up this meeting. It's really nice. It's a really nice opportunity to be all together and celebrate this Nobel Prize. So I also would like to thank the previous speakers because they gave an excellent introduction to the field. So I can rely on what they said to show a bit what we did more recently. And okay, so this is the plan of the talk. I would like to introduce first the jamming transition, then I will show some results we obtain from this replica approach, in particular about the critical exponents. And then I would like to show also an application to the problem of estimating the close packing density of spheres in large dimension. And then if I have time, I could give a few details that will be basically following up on what Sri just said at the end. Okay, so what is the jamming transition? It's something that it's very easy to define. You take a bunch of particles. The particles have some repulsive interaction, so they are like spheres. In the simplest case, you have frictionless spheres. They repel each other. So if they are not overlapping, they don't interact. If they are overlapping, they repel. And what happens is that, of course, if the density is very low, then you have, you have a bunch of particles that don't interact, so your system is floppy. If the density is very high, then they will interact a lot, and you get something that is rigid. And the non-trivial observation that was obtained, it was done mostly by Liu and Nagel and co-workers in this series of papers, is that there is a critical point in between these two phases. So you have a sharp, in the thermodynamic limit, you have a sharp transition between the rigid and the floppy states at a certain density called the jamming density. And at that density, the system has, the particles are just touching, but not overlapping, and the system is still marginally rigid. So in the case of, when you do this numerically, so numerically what you can do, you take a bunch of particles, you draw them randomly in the box, you put some soft repulsion, and then for example, you minimize the energy by gradient descent. This is what was done in this paper by Corey O'Hearn and Langer and Liu and Nagel. So, and they found this transition. And what they found is that in 3 dimensions, this happens when the packing fraction, so the fraction of volume that is covered by the spheres, is about 64%. And so this is more or less the same packing fraction that was also found previously, for example, by Bernal and by many others, using hard spheres. So if you take hard spheres like tennis balls, but very, very rigid tennis balls, and you put them in a box and you shake the box and you try to see how well they pack, they typically will pack, they will fill typically 64% of the available space in 3 dimensions. So people thought that that the jamming transition was could be also identified with the random cross packing. So the marginally jammed state, let's say the state here where particles are just touching, if these are hard particles, then they would be at random cross packing. Okay. And then there was a long debate about how to define properly random close packing mathematically, but I'm not going to enter into that. So this jamming transition is something that is observed in everyday life all around us. You can observe it in granular materials, in emulsions, in colloids, in powders. These are examples from the group of Bob Beringer of soft photoelastic disks. So you can see the force chains. Where there is light, basically there is a force. So you can see that there are force chains that are very non-trivial. These non-trivial force chains can lead to collapse of structures. So they are particularly interesting. And okay, there is also this. There are also nice board games. Like in this game, what you have to do is to remove the particles and without making the piston move here. So this is in the office of Olivier Dauchot. If you want to play it, you can go and play. And it's non-trivial because there are these force chains. So if there are some disks that are floppy, so you remove the disk and nothing happens, and other disks that are supporting a force chain, so you remove it and the thing collapses and the piston moves and you lose. Okay, so it's a very, I mean, it's an important transition that is important for many phenomena around us. I mean, of course, in these cases there are complications. There are no spherical particles. There is friction, so there is a whole lot of work to try to understand the role of all these other ingredients. But okay, I will focus in this talk on the simplest case. So monodisperse, essentially spherical, frictionless particles. So, okay, shortly after the proposal of this jamming transition as a sharp phase transition, people started to look in more details at the properties of these packings. And these are images from this work. What you see here are the force. So you prepare a packing close to in the jammed phase. So in this phase, but you approach the jamming transition from above, from the high density phase. So here is the pressure. The pressure goes to 0 at the jamming transition because there are no more overlaps. So this is at relatively high pressure. So it's kind of deep in the jammed phase, and this is close to the critical point. And what you see, what they are doing here, they are taking the particle in the center, and they are pulling it a little bit in a direction. And then they relax again the system, and they see how there is something in the chat. Sorry. Yes, I can, yes, just one second. I finish what I was saying, and then I will answer the question in the chat. So just to finish on this, so they take these particles, they move one particle a little bit, they relax again the energy to the system to an energy minimum, and they look at the display, at the forces, how the forces change on the links. So when it's red, I think the force is increasing, when it's blue, is decreasing, and things like that. So what you see is that in the far away from the critical point, you have relatively short range decay of the force field around the perturbation, while close to the critical point, you have a very long range decay, and it seems that there are like system spanning forces when you perturb in a point. So this is what you would expect at a phase transition. So to answer the question, so there was a question in the chat about the nature of these repulsive particles, of these repulsive forces. So, I mean, you can think to many, I mean, it's a general model. For example, you can think that you have a pair potential. So you have particles that interact with the pair potential. So the total potential energy is the sum over all pairs of some potential that is a central potential. And you can take a potential that is 0 when the distance between the centers is above a certain cutoff, and it's positive, for example, quadratic below. Okay. Now, physically, this could be tennis balls. I mean, if you take tennis balls, they're a bit soft. So if they're far away, they don't interact. If you bring them close, they will repel. They could be this kind of, these are disks in 2 dimensions. These are soft disks. They're made of some soft material. Again, if you push them one against the other, they will repel. Or they can be, I don't know, grains, like in this example. So, I don't know, nuts, things like that, rice, things like that. Or they could be colloidal particles. I mean, there are many different systems where you can realize something like that. Okay, so whatever system is made by kind of spherical particles that repel when they are close. But these are not, I mean, we are thinking here always to like mesoscopic or macroscopic objects. So it's not van der Waals forces. These are not atoms. I mean, van der Waals forces would give you like this R to the 6, I mean, kind of Lennard-Jones potential with repulsion and attraction and so on. And that's not what we are considering here. These are kind of mesoscopic objects. So I hope this makes it more clear. So, okay, so I was saying, okay, so we have these, people have seen numerically that there are these, close to the transition, there are these long range correlations in the forces between particles. And they also made a very nice and elegant argument that you can find in this paper and in others, but I think this is a classic references for this kind of argument. And the argument is based on force balance. So you can say, okay, the force on particle I have n particles. So I take the force on a given particle, and this is going to be the sum over all the other particles of the forces coming from the other particles, because we are looking to pair potentials. And I can write this because the potential is central. This is going to be some scalar force times the vector that connects the centers of the two particles. Okay, so the force is in the direction of the vector that connects the centers. So suppose that I give you the packing. So I give you a packing like this, and I ask you, what are the forces in this packing? Is it possible to construct? So you are given the positions. Okay, so you have these vectors, and now you have to find scalar scalars. I mean, you have to find one scalar per particle pair that is in contact, because particles have a force only when they are in contact. And you have to fix these scalars in such a way that the total force on each particle is 0, because you want to be mechanical equilibrium. So you see that given a packing, you have d times n linear equations, because the equations here are linear. If you are given the positions, these are linear equations for these forces. You have d times n of them, because you have n particles, and each particle has d directions of the force. So this is a system of dn linear equations, and how many variables you have. So on each contact, each times two particles are in contact, then you have a force. So this is going to be the total number of forces that you have is going to be the total number of contacts, which is the number of particles times the average connectivity per particle that I'm going to call Z, divided by 2, because each link is shared by two particles. So if you count in this way, if you do Z by n, this is twice the number of links. Okay, so you see that it's a linear equation with dn equations and Zn divided by two variables. And so in the generic case, in order to have a solution, you need the number of variables to be bigger than the number of equations. So you need the connectivity to be bigger than 2D. So for example, in 3 dimensions, you want to have more than 6 neighbors per particle on average in order to find the solution for the forces. And so, well, this number 2D is special because people numerically found that at jamming, you precisely have these inequalities is precisely saturated. So the number of neighbors is precisely equal to the minimum number required to have stability. Okay, so these are called isostatic packings. And so the idea is that if you have an isostatic packing, you have precisely the minimal number of contacts needed to construct forces that satisfy force balance. And so now if you open one of these contacts, so if you take two particles here and you pull them apart a little bit, which is what they do here in this numerical experiment, what would happen? You are removing one force. So now you don't have any more a solution to these equations. So your packing becomes unstable, and there will be some relaxation to a new state. So particles have to move a little bit to restore the contacts and be stable again. So you have floppy modes. And these floppy modes that you create when you open one contact are very extended, very delocalized at the transition. And this is what gives rise to this large correlation length. So the idea of this paper is that this divergent correlation length is a direct consequence of this isostaticity of the packings. And so it's related to a kind of a marginal stability of the system at jamming. So, okay, there is another question. Yes, so there is a question, what happens if the particles are not all identical, but if they have size polydispersity? And it's still true that globally the system is isostatic at jamming. So there has been work, for example, on binary mixtures or even on polydispersed systems where it's still true. So this is just, this argument is general. It doesn't use the fact that particles are all identical. It's just a linear, it's just a counting of degrees of freedom. Okay, so this means that jamming is a phase transition. It's out of equilibrium because the system is an athermal system that is being prepared in a random state, and then you minimize the energy, but you're not equilibrating in this process. I will come back on that. We are at 0 temperature. And still we have a divergent correlation length, and we have divergent fluctuations, for example, of this force field. Okay, so now what we wanted to do was to try to construct a theory of this transition. And how can you do that? So one first step is to, I mean, because we want to use statistical mechanics, at least we wanted to use statistical mechanics. One could also forget about statistical mechanics and try to make a theory, for example, based on dynamics. But we wanted to try to use equilibrium statistical mechanics because we have a machinery for that. So we tried to say, okay, let's add temperature to the problem. So let's take this system. So we have, again, these soft particles that have a pair interaction like this, for example, which is 0 if the distance is bigger than the, this should be sigma minus r, not r minus sigma, sorry. I mean, if the distance is bigger than the particle size sigma, then the interaction is 0. Otherwise, it's quadratic. This is a classical model for this kind of objects. It doesn't depend much on this potential, but let's take this as an example. And so if we add, if we consider this model, it's a liquid. I mean, if we take high temperature, this is going to be a liquid of repulsive particles. And the control parameters are temperature in units of interaction strength and the density that we can put in proper units to have packing fraction, which is the fraction of volume covered by the spheres. So we can make a phase diagram in these two control parameters, temperature and packing fraction. When temperature goes to 0, or when the interaction strength goes to infinity, the particles become very hard. So you basically go to the hard sphere limit. So this axis here at 0 temperature is the hard sphere axis. And okay, so if you are at high temperature and low density, you get a liquid. If you cool it down, or if you compactify, then you get a glass. And this is what was described by Shri in the previous talk. You have a line of phase transition between liquid and glass. Now, if you do the jamming thing, so if you take these particles, prepare them in an infinite temperature state, so completely at random, and now you quench to 0 temperature, so you minimize the energy at 0 temperature. If you do this exercise, and this was the work of O'Hearn and the co-workers I mentioned at the beginning, you are going to find a jammed state above this point, and you are going to find a floppy state below this point. So the jamming transition, this 64% I mentioned, is found inside the glass. Okay. So, okay, of course, I mean, this is an equilibrium phase diagram, and this is a non-equilibrium process. We know that when we cross this line, we are going to be in the glassy region, we are going to be out of equilibrium. But still, when we realize that, and this was, I mean, this was a long series of discussions, but you can find, for example, a discussion in this paper. When we realized that, we thought, okay, maybe what we can do is to use the machinery of replica theory to describe the transition from liquid to glass. And then maybe if we bring the glass somehow to 0 temperature, maybe we are going to recover this jamming physics. So that's what that's what I will describe next. I will come back on that. Before I move to this part, I wanted to make an analogy with a more general class of problems that are called constraint satisfaction problems. So an example this problem here is graph coloring. So you are given a graph, you are given a set of colors. Here is blue, red, green, and you have to assign one color to each node in such a way that there is no link that connects two nodes with the same color. So you don't want to have red and red here. This is a very standard problem in computer science, and it's a problem where you have constraints that you want to satisfy. So you have degrees of freedom. The degrees of freedom are the colors of the nodes, and the constraints are the fact that you don't want to have the same color in the two nodes that are connected by a link. Okay. So if you think about this problem, it's actually not so different from the problem of packing spheres, because you can think that, for example, a red node is a particle. So red particles have a strong repulsive interaction with green particles. So if you have a red particle sitting on a node, you don't want to have a green particle next to it. Okay, so it's very similar to a packing problems where you have different particles of different kind that have a repulsive interaction. And there is a very general class of problems like this one that have been studied a lot, first in computer science and then also in statistical physics, using methods from spin glasses, like replica theory, cavity method, dynamics, and so on. So you can look, for example, at this paper, and there are many other works that you can check if you're interested in this connection. But so what I wanted to mention, and here it's a reference where this is kind of described in we try to describe this in a pedagogical way, is that jamming is nothing but a constraint satisfaction problem, but with continuous variables. Okay, so instead of having a discrete variable, which is the color of a node, here we have continuous variables that are the positions of the particles, and then we have constraints that are that particles should not overlap. So we want to find a configuration of the particles such that there is an overlap, and the jamming transition is the point that separates the region where we can find solutions, so we find states with no overlaps, from the region where there is no solution, so we cannot find states with no overlap. And this is what is called in the literature on constraint satisfaction problem a sat to unsat transition. So it's satisfiable to unsatisfiable. So the problem, when you increase like the density of constraints, you add more constraints, it becomes more difficult to find solution, and you can have a sharp phase transition in the thermodynamic limit at which you cross from having solutions typically to not having solutions typically. Okay, so let me summarize this part. So jamming is a new kind of non-equilibrium phase transition that you can find in many soft matter and granular matter problems, and also in molecular glasses, but okay, it's a bit more difficult to discuss in that context. But okay, so it's challenging because it's in principle, it's an out of equilibrium phase transition, so you have to use tools that are a bit more complicated than those that you use in equilibrium. It's a disordered system, so I mean, it's kind of a glass, as she described. It's not clear what kind, is there any symmetry breaking at the transition is not clear. I mean, in principle, if you look at the structure of the packings, you don't see anything happening, but still it's a critical point. And it's a critical point, and you see a very large correlation length, which is clearly visible in the force correlations. So this is different from the glass transition, at which it's very hard to find a large correlation length. In this case, it's very clear. I mean, you look at this picture and you see that the correlation length is growing, and it's a power law of the pressure. So when pressure goes to 0, the correlation diverges as a power law. So in this sense, it's easier than the glass transition. And okay, as I just said, this is a sat-unsat transition for a constraint satisfaction problem with continuous variables. Okay, now, how do we try to make a theory of that? Building on this observation that we can use equilibrium statistical mechanics, try to construct glass states, and then go to 0 temperature. So the idea, so this is my second part, the second part of my talk. The idea is to build on what Shri described. So, and use kind of expansions around infinite dimensions. And the motivation for that is, as it happens in many fields in physics, in the case of glasses, you don't have a small parameter that you can use to set up a perturbative expansion. Because, I mean, you know, like in a system of particles, you can do a low density or a high temperature expansion. You describe the liquid or the gas. If you do a kind of high density or low temperature expansion, you can describe the solid phase by doing, for example, harmonic expansion around the lattice state. But the glass transition happens in a regime that is non-perturbative on both sides. So you cannot use density or temperature as small parameters. So you are in the strong interacting regime. Still, it turns out that you can use dimension as a control parameter. So, and this is something that has been done a lot in many other fields. And in particular, there is this paper from Giorgio Parisi and co-workers, where they were looking at QCD in large dimensions, precisely for that reason. So they wanted to have some insight on non-perturbative behavior in QCD by looking to large dimensions. And they actually found an interesting phase transition. And what I learned recently is that Giorgio, I mean, he then went to look into the literature on polymer problems to try to understand better this QCD transition in large dimension. And that's how he found that the replica method had problems in the SK model, because this was cited in those papers. And so that's why he got interested in this SK model. So there is, I think, this idea of going to large dimensions and looking to mean field limit first, that is a kind of recurrent theme in this field. So in infinite dimensions, then if you look to the glass problem, you can obtain an exact solution based on mean field theory. So and this was basically the idea of Kirkpatrick and Volines in 1987. They have this paper in particular on PRA, where they explicitly construct the infinite dimensional limit of mode coupling theory and of density functional theory, and they show that they give the same results. And then then together with Tirumalai, they realized that the kind of universality class of the transition in infinite dimension was the same as that of discontinuous spin glasses, like the Potts or P-spin glasses, as she described. And so the idea is that maybe one can use 1 over D as a small parameter and look first to the case where D is infinite, and then try to include finite dimensional effects in a kind of perturbative way. So what they did first, so in the original proposal of Kirkpatrick and Volines, they were looking to the equilibrium glass transition, so between liquid and glass at finite temperature, let's say. And then later on, they generalized their work in order to follow glassy states. So once you are inside the glass, you can follow this glass when you change temperature or density. And there is a paper again by Kirkpatrick and Tirumalai that contains some idea, and then it was formalized, I think, in a more, let's say, complete way by the work of Mona Son and again of Giorgio Parisi and Silvio Franz and Marc Mézard. So in a series of papers where they basically construct the formalism that you can use based on replica theory that I maybe will describe at the end if I have time, but I don't think so. Where you can basically construct a glass, and then you can construct a state in this region here, and then you can cool it down or increase the density and follow the evolution of your glass state. So when I started working on this problem long time ago, together with Giorgio, we wanted to apply this machinery to the case of hard spheres, and our motivation was to understand the problem of sphere packings, and in particular what would happen in not only in 3 dimensions but also in larger dimensions, for reasons that I will explain maybe later. So so we did a first version of the work, and then we realized that there was this jamming, that the close packing of spheres was more or less the same as the jamming transition for soft spheres and so on. And so we said, okay, now jamming is a critical point. So can we describe this critical point using this mean field theory in large D? And here came a lot of insight from other people, in particular from Jorge Kurchan, who had an idea of how to extend the 1RSB scheme we were using to full RSB, and from Patrick Charbonneau, who provided a lot of help to construct numerically states of hard spheres and soft spheres in large dimension, compare the theory with the simulation, and also discuss the theory and so on. And Pier Francesco Urbani, who was a strong driving force to make all this happen and do a lot of complicated calculations. So thanks to this collaboration that, here we are all together in Rome a few years ago when we were celebrating the 40 years of replica symmetry breaking, I think we managed to show that you can describe jamming using this infinite dimensional theory. And if you want to see the details, we also wrote a book that we hope should be understandable and provides a detailed discussion of all this. So I will try to give you now a quick overview of the results of this approach. And I hope, I hope to be able to give you an idea of how it works. So the idea, is again, so we start from a thermal system now, because we want to use equilibrium statistical mechanics. So let's start with hard spheres, thermal hard spheres. So now I am here in this phase diagram. I am at, let's say, at low density and very large epsilon, very large interaction strength going to infinity. So I'm basically on this line here, and I have thermal hard spheres. So my particles, what do they do? So this is a real space view. So you have particles, they are spherical, they are hard. They move around because there is thermal agitation, and they collide, okay? They collide and they are a gas because we are at very low densities. So this is a real space view. This is a phase space view. So here you should think that this can be a two-dimensional system of hard spheres. This is a view in n times d dimensions. So it's just to show that you have configurations that are forbidden, because whenever two spheres overlap, the price you pay is huge, so the probability is 0. So the white region is forbidden and the black region is allowed. So you have a kind of a bunch of configurations that are allowed, and you can move around, moving the particles around. And here you have the mean square displacement as a function of time. So this is a more dynamical view. So what you expect in a gas of hard spheres is that at short time you have ballistic motion, then you have some kind of behavior, and then at long times you have diffusive motion. Okay. And finally here, what I show here is the equation of state. So this is inverse pressure as a function of density for hard spheres. So at very low density, you have a gas or a liquid. I mean, there is no gas-liquid transition in hard spheres, so it's a fluid state. And when you increase density little by little, the pressure will go up. So 1 over pressure goes down. Okay. Now, if you keep increasing the density, this is what you see, and this is what was described by Sri in the previous talk. You see a glass transition. You see the glass transition of hard spheres. So the mean square displacement will slow down. You start to see a plateau. So in real space, what happens is that your particles are moving a little bit around in a certain region, and then they can diffuse away from that region. Okay. And in phase space, it means you have groups of configurations, and you can move around a bit there. So this is the short time motion where you rattle around some configuration, and then from time to time you can tunnel to another region of space, and you keep doing that and moving around. Okay, so this is the usual slowing down of a supercooled liquid. And if you do, and in the infinite dimensional theory, you can show that you get exactly what Kirkpatrick and Tirumalai found in their first work. So you get a mode coupling transition. So with the usual features of mode coupling, so a beta relaxation, alpha relaxation, critical exponents of mode coupling, and so on and so forth. Now, if you keep going, at some point you hit the mode coupling transition. So now if you keep compressing your system, now you are in a glass. So the mean square displacement now is completely arrested. You don't have diffusion anymore. You reach a plateau. In real space, you just rattle around. You never diffuse. So your system is a solid. And in phase space, you have this bunch of configurations that correspond to more or less to the local minima in this potential energy landscape that she introduced, that are now kind of disconnected. You cannot move anymore from one to the next. Okay. Now, of course, you could say, okay, but if I cannot move, how can I equilibrate? And that's perfectly right. So in fact, in mean field, in infinite dimensions, you would never be able to equilibrate beyond the mode coupling transition. But if you think that you are in large but finite D, you can still have a little bit of activation, a little bit of relaxation that can bring you below this point. And mathematically, you can still define equilibrium below the MCT, except that the equilibrium dynamics is arrested. So I think this has been already discussed by Sri. So suppose you can do that, and then you keep going, and at some point you fall out of equilibrium. And okay, this depends on the dynamics you choose, depends now on the history of the system, on this kind of activated processes, how they behave and so on. But you can say, okay, let's suppose I can stay in equilibrium up to some point, and then now I fall out of equilibrium. So now I am confined in one of these glasses, and I start following this glass in density. So this is one of, yes, there is a question. How many disconnected regions? So in mean field theory, this was described by Sri. There is an exponential number of disconnected regions, exponential in n, in the size of the system. This is what happens in mean field. So you can define the configurational entropy, that is the entropy of the associated to this number of regions. Okay, but this is not very important for what I'm going to discuss now. This is more important when you want to talk about Kautzmann transition and so on. But now I don't need to count the regions. I just want to know that there are regions. Now I'm stuck in a glass, and I can follow this glass out of equilibrium. So I keep compressing, And now the new thing that we realized while looking at this infinite dimensional solution with the people I mentioned before is that you can have what is called the Gardner transition. So this is a transition that was already known in the context of spin glasses, based on a work by Gardner in 1985, but we kind of found in this model of structural glass, so in Hard-sphere glass. So what happens at the Gardner point is that you have another phase transition, which is basically a spin glass transition inside the glass basin. So you are inside one of these regions, and now your region is breaking into many sub-regions, which is exactly what happens in the Sherrington-Kirkpatrick model, where this kind of high temperature regime is the paramagnetic phase and the low temperature is the spin glass phase. So this is exactly the same kind of transition, but restricted to one glass. And so when this happens, you have critical, again, your mean square displacement goes to a plateau, but it goes to a plateau in a critical way. So it's a power law. Sorry. And in real space, what you can think is that your particle is caged, but the cage is breaking in many sub-cages. So in different configurations of the system, the particle can be vibrating here or here or here. Okay. So this is something that we didn't expect, we didn't want to have, but we found in the theory. So at some point there is this transition. So you keep compressing. We wanted to reach close packing. So we wanted to reach the point where the pressure diverges because the particles are going to touch, and so you keep compressing, and at some point you hit the jamming line. Okay, when pressure goes to infinity. So when pressure goes to infinity, your mean square displacement becomes identically zero because you don't move anymore. Particles are completely stuck because they are touching. And now these are hard particles, so they cannot move anymore, they are blocked. And this means that now the fact that you are in this full RSB phase at high pressure means that each particle can be stuck in many, many possible positions that are slightly different and depend on the other particles, okay? So the interesting thing is that jamming happens inside this Gardner phase, and in the Gardner phase, you have full replica symmetry breaking. So why this is important, I'm going to explain in a second, but let me summarize. So in this infinite dimensional solution, when you take hard spheres and you compress, you have first a liquid, then you get a glass, a normal glass, but then the glass breaks into this kind of spin glass state inside the glass, which is characterized by full RSB, and it's marginally stable, and finally pressure diverges and you reach jamming. So why this is so important? Because we wanted to understand the critical exponents of jamming. So people had found, in particular, the work of Mathieu Eviard had found that there are critical exponents associated to jamming. So there is this divergent correlation length. And in particular, the plateau of the mean square displacement, this quantity here, goes to zero at jamming because particles don't move anymore, but it goes to zero as a non-trivial power law of pressure. And also he found that if you look to the distribution of gaps between particles, I will come back to this in a second, then you get a power law. And if you look to the distribution of forces between particles, then you also get a power law. So you have all these exponents. And actually, again, Mathieu Eviard and co-workers, they found that there were scaling relations between these exponents that they could derive based on this idea of marginal stability and isostaticity of the packing. But there are two scaling relations, so one exponent remains undetermined by the scaling theory. Now, when we did the calculation of these exponents using the 1RSB solution, so without taking into account the Gardner transition, we found totally wrong exponents. So it's only thanks to the fact that we realized that there was this full RSB transition in the states that we could obtain exponents that are coherent with the numerical simulations and also consistent with the scaling relations. So let me describe this a little bit better. So this is a plot of the plateau as a function of pressure. So now we have hard spheres. So the hard spheres are colliding, and the pressure comes from these hard sphere collisions. So when you reach jamming, the pressure, you are approaching jamming from the low density phase where the system has no overlaps. but still, because it's thermal, you have collisions. The pressure is finite, and when you reach jamming, it diverges because they collide a lot. Okay, so this is why here pressure is diverging. So jamming is when pressure is infinite here. And here you see the value of the plateau of the mean square displacement, which is more or less the Debye-Waller factor, is how much particles are rattling. And you see it goes down as a power law. And the black line is the prediction of full RSB. The gray line is free half, is what people thought was because people thought, okay, it's going to be a simple exponent. So it was close to free half. So people thought it was free half. It's actually not free half, is 1.41. And you see, we can distinguish the two scalings. This is an image I got from this paper of Olivier Dochot, who did an experiment in granulars, and he measured the fact that you have that the same particle, these are trajectory of one particle, and he measured that if you cycle between compression and decompression, your particle can be caged in different locations every time. So you have this multitude of jammed states that are close by, as you expect from an RSB phase. And this is the other critical exponent, gamma. So these are the gaps. So you go at jamming, precisely at jamming, so at infinite pressure. Now everything is stuck. You just have a configuration. You measure the gaps between particles, and you do a histogram. This is the cumulative histogram of these gaps. And you see at small gaps, you get the power law. And this is the prediction of the replica full RSB theory. And you see that it matches very well the numerics. This is numerics in dimension ranging from 3 to 10, but you see it doesn't depend on dimension. I will come back on that. And finally, you can take, again, at jamming, you can take pairs of particles. You can look to the interparticle force. So, I mean, if these are hard spheres, the force is going to be infinite. But if you scale by the mean, which is basically the pressure, and you take the jamming limit, you get a finite value. You can do a histogram. And again, this is cumulative histogram. You get the power law. And it matches very well with the prediction from replica full RSB. So that's to give you an idea. So to summarize, we can obtain the critical exponents that characterize jamming by taking these glassy states of hard spheres, following them to infinite pressure when they are close packed, and computing properties using replicas. We need full RSB. So this is, I think, fits well into this meeting, because we really need the insight of Giorgio Parisi to use this full RSB structure. And using that, we can obtain analytical results for these exponents that are non-trivial. And what is, I think, very surprising, at least to me, is that the predictions that you obtain in infinite dimensions work very well in essentially all dimensions. So there is recent, you can check this recent work that is the state of the art in measuring these exponents. And basically down to 2 dimensions, you don't see any deviation from these exponents. So this is an instance where you can use full RSB to get quantitative predictions for critical exponents in finite D. And I think it remains an open problem. Why? It seems that for some reason, 2 is the upper critical dimension of jamming. There is some discussion. You can check, for example, these references, but I think it's still an open problem to understand why mean field theory works so well down to low dimensions. The other thing that remains open, I think, is the following problem. So here I used equilibrium statistical mechanics. So I used an adiabatic compression of hard spheres from 0 density to jamming. But in the original formulation of Liu and Nagel, jamming was formulated in terms of gradient descent of soft spheres at 0 temperature. So if you want to describe that, you need dynamics. And now we have dynamical equations, but we don't know how to solve them. And there is the problem how this kind of full RSB structure can emerge from the dynamical equations that describe gradient descent. This is, I think, an open problem. I think Jorge Kurchan is going to talk a little bit about that. You can check also this paper where they do something in this direction. But I think it's still open. So there is work to do if you are interested. I guess, do I have 5 more minutes?
Yes, you do. Yes,
okay,
you do.
Thanks. So just I want to mention quickly the original motivation for our work, which is to understand the large depacking problem. So I told you, okay, the packing problem is the problem of packing hard spheres in space. It's an important mathematical problem. It has been studied a lot by mathematicians, and it's connected to many other problems in number theory, in communication theory, and so on. You can check this nice review by Torquato and Stillinger, where they describe all the possible applications of packing problems. And the problem is that when you go to high dimensions, so high dimensions is a particularly relevant problem for communication theory, because in communication theory, you want basically to pack signals in space in such a way that you maximize the distance between them so that you can then discriminate better. And the signal that you want to transmit is typically a very high dimensional vector. So you naturally obtain a packing problem of vectors that have many dimensions. So mathematicians have studied that a lot, but it's very frustrating because the best upper bound, so you want to know how many signals you can pack in a given volume. And the best upper bound grows exponentially with dimensions. So it's basically this. So this is a scale for packing fraction that is not important. I mean, you have to multiply by 2 to the d for convenience. While the best lower bounds are not exponential. Indeed, they are growing like log d. So you see, these are the best lower bounds. This is the best upper bound, and they are diverging exponentially with dimension. And the best packing can be anywhere in between. So the upper bound is, there is basically one upper bound that is the best. Here I put three lower bounds. This is a kind of simple one that was obtained already by Minkowski. And these two are bounds, but this one is going like d, and this one is going like d log d. So this one will eventually take over, but this one has a much bigger prefactor. So in up to dimensions that are astronomically large, this is actually better. But anyway, these are details. Basically, they are very similar. So the problem is that, so people then try to construct packings in given dimension and try to increase the dimension. But when you increase the dimension, it becomes more and more complicated to find lattices because you have many directions. And so the best, I mean, good lattice packings are only known up to dimension 128. So these are the points that are given here. And you see that if you try to extrapolate, it's very hard because you have oscillations. So the oscillations come from the symmetries that you have in different dimensions. And then it's very hard to say if this is going to saturate somehow or it's going to go up. I mean, it seems like it's going somewhere in the middle, but basically, who knows? So we wanted to try to understand what happens to to amorphous packings in large D to see if we could get an insight on the problem. And what we get from the replica method is that you can construct amorphous packings up to d log d. So you cannot do much. I mean, you can do a little bit better than the best lower bound, but you cannot do much better, okay? And okay, there is also some interesting results related to the time you need to construct these packings. That is also something that mathematicians are interested in. And I mean, I can give you details if you're interested. So, I mean, this is probably not, it's not a huge improvement, but if one could prove some of these results rigorously, like it was done for the Sherrington-Kirkpatrick model, I think it would be interesting for this problem of packing in large D. And I also wanted to mention this paper of Giorgio, where he tries to do a statistical mechanics construction of lattice packings. That is, I think, a very interesting work. So if you want to check it, I hope you like it. Okay, I had a bunch of details on the solution that I'm going to skip because they are basically overlapping with what Shri already described quickly at the end of his talk. But so if you are I mean, basically, the only thing I wanted to mention is that you can construct this full RSB for this hard sphere problem in infinite dimensions. You have equations that look like the ones of the Sherrington-Kirkpatrick model. And basically, the critical exponents emerge because you have, when you go to jamming, you have a scaling regime like in the SK model, except here is different. You have free exponents that you fix by fixing some kind of boundary conditions that are related to the marginal stability of the packing. So this is something that is explained, I hope, pedagogically in the book, in chapter 9 of the book. So if you want to check that, you are welcome, and I'm happy to answer any question about that. I mean, if you want to write me an email later, if you have any doubt on this, I'm very happy to discuss. So with this, I want to conclude. And so jamming, I think, is a nice source of inspiration to do nice mathematics. it is connected with many real-world problems, packings, constraint satisfaction, granulars, soft matters, and so on. And it's a kind of a new universality class of full RSB systems because it has different exponents from the SK model. And it seems to work very well down to 2D, which is very, very interesting, and I think should be better understood. So thank you very much for your attention. And of course, I take this opportunity to congratulate Giorgio for the prize. Thank you.
Thanks, Francesco, for another wonderful talk. Shrikant has already raised his hand. Shrikant, would you unmute and ask?
Yeah, so thanks. Thanks, Francesco. That was a lovely talk. I had sort of two clarifications to seek. One is, when you compare the glass transition line versus the jamming line. Yeah, if you can go back there. Yeah. So, I mean, if you're sitting at some density between 5G and 5J, you are rigid at finite temperature, but you're not at zero temperature, right? So the thermal agitation gives you the rigidity, which I mean, it might be counterintuitive with many people. So
yes, you're right. No, you're right. This is a very good point. So I mean, if you look to the, so this is discussed. I mean, this was a very interesting observation that was, I think, basically done by Hajime Yoshino, who had worked a lot on rigidity. And the point is that exactly, so if you look, for example, to the shear modulus or the bulk modulus, because they are both scaling the same way, if you are in this regime, you have a finite shear modulus because it's a solid, but it's proportional to temperature. So it will go to zero when temperature goes to zero, while here, the shear modulus is going to a finite limit where temperature goes to zero. So you can think to the zero temperature limit of the shear modulus as a kind of an order parameter for the jamming transition. And you can study the scaling of the shear modulus, and the critical exponents that appear that I showed you also appear in the shear modulus, so you can measure them directly from the shear modulus. So yeah, that's a very important point. I'm sorry that I overlooked it.
So the other thing is, right towards the end of, actually on the last slide of your talk, you mentioned all these other problems, and you said the practically important problems. So I just want you to say a little bit more for some of these, things like the constraint satisfaction, etc. The high dimension is not unrealistic, right? This is actually I mean, these are the kind of dimensionalities you have to think about. Is that correct?
Yes, yes. So in particular, okay, you can check. So you can think, for example, the perceptron problem, which is the simplest, or you can, I think people now know better deep learning machines than the perceptron, but the perceptron is just a deep learning machine, which is not deep, which has only one layer. Anyways, if you think to one of these deep networks that now we are all familiar with, these are systems where you have a lot of parameters. That are all the weights in your neural network. And you want to train your neural network by showing examples, and you want the neural network to classify examples. So you can think that you have variables. The variables are the weights in the neural network, and you have constraints, and the constraints are that the neural network should tell that a cat is a cat and a dog is a dog. So you try to classify, and here, so now the jamming, you have a jamming transition precisely as in the packing problem or in the coloring problem, which is the point at which, when you show more and more data to your network, at some point the network has not enough parameters to classify perfectly all the data. So the training error of your network is going to be zero when you have few data, because you can fit all of them because you have many parameters, and it's going to be non-zero when you have a lot of data and few parameters. So you have a jamming transition as a function of the ratio between number of data and number of parameters. And well, there is a debate, hot debate, I think, in the community now. So how, this jamming transition is important for the performances of the network, like generalization and things like that. And so for this, you can refer to the work of, so Mathieu Viard has a bunch of papers on that. And also I think Lenkas, Deborah and Florent Chakala, they have a bunch of papers on that. So you can refer to their work for more details. But yes, it's something that is now appearing in many different contexts like machine learning. And I mean, of course, then in granulars and in soft matter problems is a very important issue. But
Thank you.
Thanks, Shrikant. Thanks, Francesco. Professor Francesi has a question. Could you please ask? Yeah, thank you. You have to unmute yourself, yeah.
Yes, I'm trying to.
Yes.
Okay, thank you. So very nice talks so far. I want to congratulate to everybody. And I'd like to ask to Francesco a clarification for me. Maybe I missed the point. If you go back to the same slide that Shri was asking you to show, sorry about that. When you are mentioning, you see, the TG, the glass transition, of course, you say that it is a glass transition, a phase transition, but that's only strictly speaking true in infinite dimensions. Is it right, or am I missing something?
No, you're totally right. I'm sorry about that. So in the infinite dimensional limit, in the mean field limit, you have a sharp glass transition that is basically this mode coupling transition where dynamics becomes arrested. In finite dimensions, we have many arguments based on theory, but also direct evidence from numerics and from experiment that this is not a sharp phase transition, it's a crossover.
It's dynamic.
It's a dynamic phenomenon. So the point is that indeed, that's what I was mentioning before. The glass transition is a very difficult problem because when you are in 3D or in 2D, even seeing a growing length, a growing correlation length is very difficult. I mean, people have evidence of some growing length, but the length grows from 2 to 4 particle distances. It's not growing much. So, I mean, what happens here is very complicated. So if you want, in the mean field limit, you have a sharp phase transition here, and you have a sharp phase transition at jamming. When you go away from in field, this one becomes very broad. I mean, becomes a broad crossover, but this one remains as a sharp phase transition. And it seems that non-perturbative effects are much stronger in the glass regime than at jamming. So this is something that has to be, of course, understood. So what I discussed today was only essentially the mean field limit. And there is a lot of work to do to understand how finite dimensional effects impact the physics. Thanks for the...
So, just as a point, is there any connection with vanishing Griffith's temperature transition that is related to the higher, you see, derivatives of the free energy? That was somehow considered in some version of the Potts spin glass model. Those that were in which there was a coupling between a Potts variable and a Ising variable. And in that case, you could have this vanishing Griffiths transition that is basically related to the, not the second derivative of the free energy, but to the, you see, higher derivatives. And
I don't know. I mean, in here, I mean, when I talk about jamming, again, it's basically what you see in 2D is the same as in infinite D. So you don't. I don't have the impression that there is any kind of like fluctuation, like effect that is relevant in that case in finite D. So I don't think that Griffith's phenomena play a role there, but maybe it could be, and I'm missing that. Around the glass transition, I mean, yeah, all these kind of things can play a role. So, and I think the problem is
yes, you know, I was referring to the transition. Indeed, no, I was referring to the glass transition, right?
But I'm
some
happy to discuss this.
Lens that is diverging. Okay. Yes.
Okay, thank you. Smarajit and then Chandan.
Yeah, so Francesco, so you talked about Gardner phase, but is there some experimental evidence or even is there simulation evidence in finite dimensions? There are some controversies, right? That initially there were yes, and then some suddenly.
Yes.
No.
So
what is the current scenario?
Yes. So I think it's still an open problem. So in infinite dimensions, there is for sure a Gardner phase, and that's in the mathematics, and so we know it's there. And the point is that we need it to obtain the right. But of course, this doesn't mean that in finite D you still need it. I mean, essentially, we have a path to get to the right criticality of jamming going through full RSB, but maybe there is another path that avoids full RSB and still gives you the same criticality. So the current status is that we have numerical simulations. So I would say in art spheres, it seems to be visible. So we have numerical simulations and there are experiments. So the experiments are the one of Olivier Dochot that I cited here. And there is also an experiment by Eric Corwin and co-workers that is cited in the Nobel Prize motivations to Giorgio. I forgot to add it here and I'm sorry, but I can give you the reference. So I think in the art sphere case, we see a finite dimensional version of the Gardner transition. Again, it's the same problem as spin glasses. So it's never a completely clear-cut thing because I mean, it's because of, I mean, basically you have the same problems that you have when you do experiments in spin glasses, but we see something. I mean, we see a divergent spin glass susceptibility and things like that. When you go to glasses that are like Lennard-Jones glasses at high density, so in the regime where you don't have jamming, you just have an harmonic glass. In that case, we don't see a clear signature of the Gardner transition, but still there is this work of Francesco Urbani and Giampaolo Folena, who proposed that there could be a different, again, another universality class for the Gardner physics that could result in a non-divergent spin glass susceptibility. So I think there is still something to be done. So if you are interested, I'm happy to discuss this in private later.
So soft potential is somewhat, it's somewhat hidden in some sense, or a different version of it compared to a hard sphere.
Yes, so in hard spheres is more visible. We see in simulations, we see a growing spin glass susceptibility. Then it's hard to say if does it diverge or not. But in structural glasses like of the Lennard-Jones type, maybe it's not there, or maybe it's there in a different form. So I would say there is a lot to understand also in that case.
Okay. Thank you.
Chandan?
Hello, you can hear me, right?
Yes.
Yes.
Yeah, very nice talk, Francesco. I just had a question about how general these results are, in the sense that one can observe jamming, for example, in the presence of shear. Or these days, people are looking at active forces, and then again, there is a jamming transition when you have active forces in the system. So do you expect sort of similar scaling behavior for all those systems?
Yes, so the machinery, let's say, the machinery that is described in this book can be applied to the case of shear. So we have, there is a chapter at the end of the book, and we have a series of papers with Hajime Yoshino and Francesco Urbani and other co-workers, where we use this machinery to add shear and see, for example, in some cases you can show that you have shear jamming and things like that, and the critical exponents seem to be the same. The active case is very interesting, but it's more difficult because in that case, we need to really use dynamics because the system is really cannot be taught as a glass state that is being adiabatically like compressed or strained and things like that. And so for the moment we are not able, I mean, we have the equations, but we cannot solve them. But I mean, in principle, the machinery of this infinite dimensional thing is something quite general that you can use for whatever potential you want, whatever physical situation you want, except that then you can run into technical trouble. I mean, when you have equations that you don't know how to solve. But yeah.
So it is not clear, for example, in the active case, whether the same exponents will be there or?
Yeah, that's a very interesting problem that for the moment, we were not able to solve. We have been trying for a few years, but we need to solve the dynamical equations. And I mean, also I forgot to mention that also without active forces, just the gradient descent, there are the critical exponents that I described that are kind of static critical exponents. So they are related to the structure of the packing, but there are also dynamical critical exponents. So the gradient descent has a divergent time scale when you approach jamming, and that divergence as a critical exponent that must be obtained from dynamics. And for the moment, we were not able to obtain it because you have to analyze these dynamical mean field equations that are complicated, and we are working on that. But so if someone has ideas, we are very happy to talk because we are a bit stuck. on that. So yes, I mean, understanding, for example, how the viscosity would diverge at jamming, how the relaxation time, all the dynamical criticality is still an open problem.
Okay, thanks a lot.
Thank you.
So one more related question, just 1 minute, 1 second.
Yeah, sure,
So
sure.
is there some sort of suppression of fluctuation near jamming such that that all mean field like theory somehow works?
Yeah, that's more or less the idea of these works. Here you can check these works. So the idea is that if you look to the fluctuations of the force, like if you could make kind of a S of Q, I mean a density, a static structure factor, but not for positions, but for forces, you find that low Q behavior is suppressed. And so there is some kind of hyper-uniformity in the space of forces. And maybe this is what is responsible for the fact that mean field still works in low D. But I mean, I think these works are nice, but I would like to have a more like detailed understanding of that. So I think, yeah, that's the idea, but I would like to understand it better.
Thank you.
Thank you. Thanks, Francesco. Thanks a lot.
Thank you very much.
Yeah, very nice talk.
Yeah,
Thank you.
thank you.